In the polarizing filter experiment, the behavior of light passing through polarizers suggests a quantum system because the outcomes align with principles of quantum mechanics rather than classical physics. Here's how orthogonal measurements and vectors come into play. 1. Orthogonal measurement. When a polarizing filter is oriented perpendicular, orthogonal, to the polarization of light, no light passes through. This corresponds to a probability of 0 for detecting a photon in a state orthogonal to its initial polarization. This discrete outcome, light is either fully transmitted or completely blocked, is characteristic of quantum systems, where measurement outcomes are probabilistic and governed by the squared projection of the state vector onto the measurement basis. 2. Quantum state vectors and superposition. The polarization of light can be described by a quantum state vector in a 2D vector space, e.g., horizontal and vertical polarization. When light passes through a polarizer at an angle relative to its initial polarization, the amplitude of the transmitted light is given by the projection of the state vector onto the axis of the polarizer. The intensity of the transmitted light, proportional to the probability of transmission, follows Malice's law. Intensity equals initial intensity times cosine squared of the angle, where theta is the angle between the initial polarization and the polarizer axis. This reflects the quantum mechanical principle that probabilities are given by the square of the amplitude of the projection. 3. Quantum interference. If two polarizers are aligned at an angle theta, and a third polarizer is inserted at an intermediate angle, the light that initially could not pass through the second polarizer can now partially transmit. This is due to the superposition of quantum states, where the intermediate polarizer changes the basis of measurement. 4. Distinctly quantum behavior. Classical particles would either pass through or not based on their orientation relative to the filter, without any probabilistic transition dependent on intermediate angles. The probabilistic nature of transmission and the dependence on vector projections are uniquely quantum mechanical features. Summary. The quantum nature of the polarizing filter experiment is evident from the use of orthogonal measurements, where certain states yield zero probability of detection. The mathematical description involving state vectors, projections, and probabilities, which directly align with quantum mechanical principles.